All right, in this video, I am going to explain angular momentum in human movement biomechanics, okay? I'll try to explain what it is, why we should care, and then, what are some of the things that's being done for it in terms of research. Comment down below which minute you got lost at, all right? And then we'll see how many of you can get to the end of this. But let's start. What's momentum? Why do we care about momentum? What's the deal with it? If you paid any attention and weren't sleeping in your physics class, linear momentum is the most simple. It's a quantity, it's a physical concept that it's defined by the mass of an object. In this case, let's look at this basketball, and then how fast it moves, okay? I like to describe it as it quantifies the oomph to a movement. So listen to the sound of this ball dropping onto the floor, all right? So let's say I release it from this height. It hits about that hard, produces that amount of sound, which corresponds to how much energy it has. That's the oomph of the movement. Now, how do I make that oomph go louder? One way would be to throw it to the ground harder. Right? It's louder, has more energy, more momentum, more oomph. Now, what's another way you can get more oomph? Well, add more mass. Imagine if this is like a solid, firm, heavy stone ball. I'm gonna get kicked out of the gym, but it's almost gonna be quite loud, right? That's linear momentum. It makes sense. If you get lost until here, nobody can save you, all right? Number 2, angular momentum. Why should we care about? You know what? Let's go back. Why should we care about linear momentum to begin with? What the heck is it about? Well, one of the most important things about momentum as a whole is it tells us that it's not only the motion of an object that you should care about, but also how much stuff you're moving. And think about it in running, in jumping. You are moving your body, your whole entire system, not just my big upper body, but also the lower body as well. It always adds up together, and you have to move it all together, right? So when you think about how fast you want to run, how high you want to jump, there's a reason people talk about fat don't fly. Heavier people, it's harder for them to run fast because it's more mass they have to move. You have to get your body at speed, and you have to change your body's momentum to go from one place to the other by applying force to the ground. Obviously, the heavier you are, the more momentum you have. Staying around or whatever, the more force you need to apply to get you going somewhere. That's why momentum matters. Everybody loves to look at just motion or speed or jump height, but really it all came from momentum. In that case, linear momentum. Great. All right, if you got lost at this 3-minute mark, watch that again, because I think I did a pretty good job. All right, number 2, angular momentum. What is it? Why do we care? The same way we want to know how a body, we want to study, understand how a body translates through space. Linear momentum does that very well. You want to understand jumping high? Understanding linear momentum tells you pretty much all you need to know. Obviously, there's many other sub-components that goes into it. Angular momentum, it's the analogy or the equivalent in terms of momentum for linear. So if you want to look at linear motion, linear momentum is like mass and the linear movement that something is going through. Angular momentum tells you that how much oomph you have in terms of rotations, right? If you go to a simple physics textbook, it's going to tell you this thing. Angular momentum of a ball, it's going to be the moment of inertia, crazy sounding word. But think of it as how much an object doesn't want to be rotated. Like if you have more inertia or more moment of inertia to overcome, it's going to take more to spin at the same rate. Think about how easy I'm spinning this basketball on my finger. Oh, that's pretty good. Look at this. Trying to spinning this instead, imagine a concrete ball, right? How much more twisting do I have to do to get it spinning? Same thing as if you want to throw a heavier ball, you're going to apply more force because it's heavier. And you throw even harder, and it goes around the same speed, even though you exerted more force. Same thing, if it has more moments of inertia or more resistance to being spun, then I need to apply more torque or more twisting force to get it to rotate, right? That all seems pretty and dandy. But that's not all for angular momentum. One very important distinguishing factor in human movement biomechanics is that if you want to understand the angular momentum of an entire system, aka throwing a baseball, or in this case me launching the hell out of this basketball, it's not just the rotations of the ball, obviously, right? Because my body also has to move through space. Now, where do I generate all of this momentum for each of our body segments that let us launch the ball? It has to come from somewhere. Let's go back to linear first, okay? When we look at linear momentum of the entire body, it came from the summation of the movements of the entire body segments. Feet, shank, thigh, pelvis, trunk, head, arms, all of those, and the ball or whatever implement you're throwing, right? The linear momentum of all of those, that's what our pushing against the ground can change. Similarly, through us interacting with the ground, we can also change our body's angular momentum. But what's important to know is that the angular momentum about the body, or we call it angular momentum about the body center of mass. So center of mass is a summation. Actually, I did make a video before about center of mass, so go watch that. But center of mass is a weighted sum of all our body segments. Let's think of it as a balancing point, where if you align your center of mass and if I'm that person and you try to pick me up and you sort of balance me on like a pointy part, center of mass is where everything will be balanced. That's why we call it the weighted average, right? It literally is the average point of all of the body segments, masses on my body. So that's why you usually use that as a convenient reference point for angular momentum. We can say, we can describe angular momentum as relative to a particular point. Why is this important? Why can't we stick to moment of inertia times rotation? That's because, let's think about it. I'm going to rotate my torso at a specific speed and then try to launch the ball, right? The only difference being when I'm launching and rotating like this, I'm going to hold my hand out at around this angle. So basically my upper arm is vertical, my forearm is horizontal. I'm going to rotate in this direction. That's number one, case number one. Case number two, I'm going to do the same thing. I'm holding out here. And I'll try to make sure that my speed of rotation is the same. If the speed of rotation is the same, that means the angular velocity of my arms is going to be the same. But the only difference will be how far away the ball is to my center, right? Obviously, if I extend my arms out, it's going to be longer. Comes in, it's going to be shorter, okay? So let me fix the camera and then try to launch this ball. Shout out to my portable charger for messing this up very nicely. I just unplug it, there you go. Okay, so I'll come here. I'll try to rotate the same speed. 1, 2, oh, great. 1, 2, 3. Okay, how about that far? Now let me try to do the same thing, but with the arms out. 1, 2, 3. Oh, it's a little further. Why is that? Now there's a very obvious reason, very intuitive reason. When you hold something further away from you, obviously you can throw it farther, right? That's the whole point why. When we're throwing, we actually all end up looking like this. Our arms are extended, right? They're long, they're far. How do you quantify that? How do you fold that in? Everybody describes throwing something as a rotational movement. How do you account for, this distance with angular momentum? Because what you want to also account for, obviously, how heavy someone is. If you are into the baseball world, you might say, being heavier, bigger, taller helps you throw further. Why is that? There is literally a mechanical reason, because all of those factors I just mentioned, they go into computation, the true computation of angular momentum about the body center of mass, okay? Go back to 1980 something, Jesus de Pina, high jump biomechanics researcher. He literally computed angular momentum about the body center of mass before high jump, because in high jump, you need to create rotation, like John Evans called it the somersault. Not John Evans, but Jesus originally, Jesus originally called it the somersault of angular momentum, because there's rotation of the entire body about the body center of mass that helps you get over the bar. In baseball pitching, there's rotation of the whole body, but the goal is different. Let's talk about the goal. What is the goal? You want to launch the thing. You want to launch the ball, right? And launching the ball means you want to impart a very high linear momentum for the baseball at ball release. And how do you do that? You do that through a sequential rotations of body segments into the baseball world again. Well, all that means is the body segments rotate in sequence such that it resulted in the ball having a very high linear momentum. But body segments rotation, that's not all it's doing, because of how our body is a linked chain segment, right? If one, but because they're all connected, I move my upper arm a little bit, the forearm is going to be dragged along with it. And that's not even like the relative relationship between the upper and the forearm. So let's say I fix my elbow angle here. I fix it, so I'm literally only moving my upper arm. But guess what? Because this angle is fixed, my forearm is also moving. So every segment, as it moves through space, it's going to result in the movement of the next segment. That's why when we are studying how the segments rotate, in terms of like what it does, that results in angular momentum being generated and then the ball being launched. We cannot only look at how the segment is rotating in space. It's not just about this. There's also the whole, the whole translation of the linear movements of the body segments brought on by the fact that we are a linked chain, meaning you have multiple segments connected together like a link, right? The name should make sense. Linked chain. That's how we are moving, how we are throwing. So there are two things you need to consider when we are trying to quantify how much oomph a rotational movement like this has. Obviously, number one, this is the most intuitive part, how much the segment's rotating in space, right? How much the one thing is spinning. But the other part, which in research, my own research as well, has been shown to be way more important, way larger. And that is how much these, especially the more distal, the further away body segments, how much they are moving through space linearly, how much this linear momentum has. There's a cool fancy equation that again you can find in the original paper. I'll try to link for this YouTube video. But there should be two parts. It's not just, they're not rotating in space on its own. It also moves through space. And mathematically, you need two terms to quantify those different behaviors. They're different mathematically, but they all happen together. They happen together because that's literally how our body works. It's a link chain. And when you're an engineer, you study link chains like machinery and stuff. You use those things all the time. You quantify it all the time like that, okay? So yeah, that sort of explains, what it is. Why should we care about angular momentum? Just to wrap it up. Why do we give a shit, okay? I've been asked that question a few times. If you've been lost at this point, it's fair enough. Angular momentum, even people in the field struggles with it at times, if it's not explained well. To me, given my background, which I studied how interactions with the ground results in changes to the body, because that's literally how you generate movement. You push against the ground in different directions. That's both true for linear movements and for rotations of the whole body. And that will be another long video, which again, if you go back to watch some of my presentation videos, hopefully that helps, but if not, I can make another long form to explain it. You care about angular momentum because A, you can literally study how it's being generated, how it's changed through interactions with the ground, okay? Everything's causal here. You don't need to rely on correlation and then have somebody complain about correlation doesn't equal to causation. All of these mechanics stuff is causal. The way you interact with the ground directly influence how your body's angular momentum, angular oomph, how it changes. That's number one. Number two, it accounts for how long your body segment is, how heavy they are, how fast they're moving through space, and against how far away you are throwing. And all of those directly result in linear momentum of the end effector, aka in this case, basketball, baseball, whatever throwing implement you have. It includes all of those. It's so comprehensive. It's not just, rotational velocity of this body segment at this time point or whatever. It literally encompasses everything because momentum is such a fundamental measure in terms of physics. One metaphor I've started using the past year when I was sharing this like academic conferences is that think of the Earth's rotation about the sun. In this metaphor, the Earth is any one of your body segments. And the sun is the body center of mass. Earth spins its own axis because the Earth is a sphere, not flat, okay? Let's make that clear. And then Earth also orbits the sun, right? Earth's own rotation is like this, like spin, and the rotation about the sun is like this. Those two motions or movements combined gives you the Earth's total angular momentum about the sun. Now, when you want to do all of the body segments, the angular momentum of the whole body, you can literally add them up together by computing angular momentum of every body segment. And that tells you literally the rotational state of the entire body. Super nice, all right? So hopefully that helps clear up, not clear up, but like just literally teach and explain what angular momentum is in this one video. I don't think I'm gonna cut it because, 17 minutes is quite long. But if you made it to 17 minutes, drop a poop emoji at the bottom, okay? And then I'll give you a thumbs up for the poop emoji, and that tells me, you're in for the joke, all right? I have to go back to work, but I really felt like I needed to explain all of this. Somewhere, a lot of this niche biomechanical concept being out there, which is great because it means I have a job. I'm gonna have a job when I graduate, unlike many other regular BME graduates who's trying to get into pharma. Sports biomechanics, angular momentum, all that stuff. People get confused by it in the field, outside the field, in physics class. For me, I don't think I fully figured it out, but I have a pretty decent grasp at it at this point. But yeah, thank you for watching. If you watched to this point, and I'll stop the video right here. I'll see you probably next week for my daily updates. All right. And let me know if you enjoy these long form videos, and we'll go from there.